Okay, so in a simple circuit here where you have the power source, we call it volts, okay? That is the EMF or the volts, right? This is the resistor, and of course you have the path, which is the wire, okay? So if you have, for example, a power source and you take out the resistor right there, what's going to happen is the current, well, current is going to come from the positive, right? There's your current flow. The current flow is going to just go through that wire. If there's no resistor, what's going to happen is there's nothing to use that current. It's going to have to go back with the same amount. But what you want is actually for the I to be used up. So the current has to be used up, right? But it's conserved. It's using it, but it spits it right into the path for it to go back, right? It's conserved, so the total current is back to where it started. However, the voltage is completely used up all the way to 0 volts when it goes back to the EMF. Okay, we'll learn more about that. Okay, so yesterday we talked about the analogy already, so I'm going to switch now to the next page. Okay. So yesterday we talked about the heart, the human heart, for example, okay? So your heart is kind of like the power source. Your blood vessels would be the path, and your cells would be the load. So we are a circuit. Okay, moving on.
They take more time, or this
Without the resistor,
no, if
if there is a resistor there, so the current then will basically get slowed down here. It will slow it down.
this takes time,
It will take time. Yeah.
but the power is not destroyed.
Which one? The voltage? The voltage will be completely gone. Yeah, it will be destroyed. You could think of it. You could say that, let's say you have 120 volts and there's only one resistor. When you turn this resistor on, the volts then will go from 120 volts. It's going to kick out 120 volts and it's going to drop it into here. And it's going to go back as 0 volts. So that's how it starts. So your whatever volts you have here is going to go feed into all the resistors that you have and come back as 0 volts. So voltage is going to be completely used up. You're going to learn later on what exactly is voltage. Well, voltage is basically what kicks the electrons out. Okay, so the current is the result of the electrons getting kicked out, but the volt is what kicks it out. Okay, so eventually it's going to be used up by the resistor. There's no more kick. It's basically just making it go back to the home base, the battery, AC or DC power source. Okay, it's all gone. The current is going to be the same. So let's say you have 10 amps. Let's just say you have 10 amps. The 10 amps will then be used up here, but it's going to spit it right back up, and it's still 10 amps right here. It's conserved. Yeah, so the charge, the current is conserved. So every single point is going to be receiving 10 amps along the way. But the voltage is used up, gone.
Use it up to 0, I mean.
Yeah, it will use it up until when it goes back to the battery, the negative side of the battery, that volts is 0. Okay, we'll learn more about that. Okay, so this is Ohm's law We talked about Ohm's law yesterday in the other booklet I was using, so now let's get right into here. So here's the circuit schematics. So the symbols that you're going to be using when you're drawing circuits in circuitry would be these ones, okay? So here again, this would be a series of battery. So there's you got positive, negative, positive, negative, positive, negative. You could imagine if this is a battery, how many batteries do you have end to end here? In my drawing, you have 3. You guys know in your flashlight, right? Say for example, you have a flashlight or you have any device. We're going to be doing a lab tomorrow. You have a battery. And sometimes you need more than one, right? So you put them end to end or side by side, but it has to be positive, negative, positive, negative. You guys know that if you have, for example, you have a compartment where you have, let's say you have 3 batteries inside. You know how you connect batteries? Do you put all the positives at the top? Would that work? It's not gonna work that way, right? So let's say this is the positive and this is the negative. What would be right here? This will have to be negative, this will have to be positive, this will have to be positive, this will have to be negative. So it basically is flowing. See here's how it works. The current goes this way, and then that way, and then that way. Okay? So you can see that the current always goes from positive to negative. So you need to connect batteries that way. So this is a battery. This would be a DC supply. What is DC? DC means direct current. That's what DC is. So that would be good for portable, and this is the product of Thomas Edison. So Thomas Edison was a big battery guy. He talked about DC, or direct current, as the power supply, and that's what he was pushing for, whereas Nikola Tesla was pushing for AC. So this is the AC, or alternating current. So that's what AC stands for. Okay, there is a big difference, and we're gonna talk about that more in details. So that's just a wire. This is a wire with a connection. So this is a switch. So if this is not touching, you see here the bridge is broken, this is switched off. Okay, if this is down like that and it's touching, so you basically have put that down, this will be switched on. So basically the electrons need a path. They need a path, which is the wire. So it has to be completely in contact. If you have a contact point that is not completely touching, you could get an electrical short circuit, okay? Or it's not gonna work at all. All right, so some of the things here that we use to measure things, okay? There's a galvanometer, you're gonna see that. Galvanometer is great for measuring voltage if it is connected in parallel, and it can measure current if it is connected in series. So it can measure both, but galvanometer is good only for measuring small amounts. So I'm not going to use a galvanometer if I'm measuring the volts coming out of the wall, for example, because that's 120 volts and high amps, right? An amp meter or an ampere meter, also known as ammeter, this is always connected in series, always. What do you think an ammeter measures? Amps, which is, it measures current, right? A voltmeter measures voltage, right? And it's always connected in parallel, and there's a big reason why. You'll see later why it's in series and why one is in parallel. And this is what I call the monster fangs. You see that? They actually do look like vampire fangs, don't they? I call it monster fangs. They are the resistor. Okay, these are the load. Capacitor, okay, it stores charge, which is very handy. Here's an inductor, and this would be a diode. I'm gonna add one more thing here, something like that. This would be a light bulb. So if you're gonna be more specific, you can use that to differentiate between a light bulb and just an ordinary resistor. Okay, so
like a different symbol for the light bulb.
There is, but I can't draw it. So it's basically like that. So those are the circuit schematics.
So I have a question.
Mm-hmm.
What happens if you connect like the other booster in the car?
Mm-hmm.
If you connect positive and negative, and then you take that wire and it touches each other, like the
And they touch each other,
Yeah.
like the positive and the negative.
yeah.
Well, then it will be short circuit. The electrons then will take that path instead. So it will be, the electrons will go, oh, there's a connection here, there's a path, then I'll take that one instead. So you can have a short circuit. That's why it's called a short circuit.
So is it like gonna explode? What's gonna happen?
You could basically short circuit. It's not gonna get to the battery that you're trying to boost.
Yeah, I'm saying like you connected one car,
Mm-hmm.
but you have the wire. You didn't connect the other car, but you have it. So the
Oh, I see. So
so
one end is already connected to the battery that is working.
yeah.
And then so the other one you're gonna connect to the dead battery,
Yeah,
right?
but-
What if you didn't connect it
But
and you put it together
No, it touches.
and it touches? Then basically it has a resistance itself, right? Every time you have a wire, the wire itself has what we call internal resistance.
Right.
So the current then is just going to go from the positive terminal of that battery, coming from the car battery that's working, and then go through the two wires that you touch and then go back there. So it will be a live wire. You can electrocute someone with it.
Like
It's
you
12
have
volts.
it in your hand, so is it gonna affect you?
It will electrocute you if you're holding the metals.
Right.
You bet. Yeah. So if you put it into a battery and you turn on the car, the battery, so then what happens is the car actually will turn on the ignition and all that, and the battery will turn on, right? You can get electrocuted. You bet. You can electrocute someone with that. So yeah, it's just an X. I use that one. You can use that too.
I used to use the other.
That one right there. Yeah. So that's a light bulb. There is another one that they use for actual blueprints. Probably just as easy. Okay, let's do a simple diagram, and then we're gonna put together Ohm's law, circuit schematic, and then you're gonna learn one more thing. It's called Kirchhoff's rules. Okay, so here's an example of a circuit. So a flashlight is a simple example of an electric circuit. You have two 1.5 volt batteries. So we're gonna start, we always start with a battery. So you got two of those. There you go. Placed in a flashlight, the total voltage is equivalent to 3 volts. So I'm gonna put the EMF here. So you would put the number of volts right by the battery or the AC or the DC, right? This is a DC. A typical current for such a circuit could be 0.4 amps. So a possible diagram for such a simple circuit can be, well, this is just a flashlight. So here's your light there. You can also go like this, like that. Okay, so there's your light or a resistor, but in this case it says it is a flashlight. You could put the this anywhere. It could be here, or the resistor could be here or here. Okay, it doesn't matter, as long as it is in the path anywhere. So I just put it right there on the bottom. So there's a circuit. Okay, so you got the three parts right there. You got the power source, got the path, the wire, and the load. Okay, now let's get to lesson 3, because this is when we actually learn how to draw a series circuit and a parallel circuit. And then we're going to start calculating the volts, current, and the resistance. All right, ready? Moving on, page 14.
So we don't need to what about the amp and the current?
Yeah, so this would be the amps. So then when the current goes this way, the total current here is going to be 0.4 amps. So this load is going to take how many amps, do you think? So the current's going to go this way, Okay, it's gonna be slowed down by this resistor. So what's gonna happen here? Gonna spit it right back into the system. So what goes, how much current do you think is gonna be in this wire? So if 0.4 amp is running in this wire, you're gonna get 0.4 amps running here, and then the I here is also gonna be 0.4 amps because there's only one. What do you think if you have two identical light? What do you think would happen to that 0.4? It will split it. It will split it. It will divide it by 2. If it's identical, each one will take 0.2 amps. Okay? If they are identical. If they're not, then we're going to have to figure out another way to do that. What happens to the volts? Okay, so the 3 volts now, in this case, is going to go out this way, is going to be going with 3 volts, right? How much volt is going to go into the light bulb? Well, it's going to use up 3 volts. And what is going back here? 0 volts. Okay, so that's what we know what happens here is that the current is conserved, whereas the volts is completely destroyed. It's gone. Completely gone. Used up.
So in the middle it can be like this.
It can also be like that, like this one here.
Like this,
Yeah. You could also, you can draw it many different ways. You could draw it this way as well, where I put my light right here instead, and put it anywhere you want.
The flow is from
Positive to negative. That's the flow of current. That's a conventional current flow. Whereas, what about electrons? The electron is going to come out of the negative side. Okay, remember we are going to trace the conventional current flow. Is the current that we're dealing with. Okay, the electrons move, but it is the current that's going to be the one that we measure. So, okay, so far with the basic principle, okay, you're going to see more of that, what happens to the volts, what happens to the current, and the resistance as well. Okay, so a circuit, circuits have, can you guys erase this for now, for a second? Series and parallel. We're going to talk about network later on. I don't want to even bring that up right now. So there are 2 types of circuits. 2 types of circuits. Series and parallel. So those are the 2 types, series and parallel. So how do we know which is which? Okay. Connections. How you trace the flow of current. That's how you know. Okay, so the diagram below shows a circuit in which 2 resistors are connected in series. Okay, so let's draw one in series. This time I'm gonna put the volts on the side. Okay, so I'm gonna put R1 and I'm gonna put R2 right here. You can do it many different ways. You can also go like this. Okay, there are so many different ways that you could do your circuit schematic.
You can stick to one, right?
You can. And how do you know which is which? I'm about to tell you now. Okay, so here's your volts, right? There's your volts. How is the current gonna be coming out of? Positive to negative, right? So here's the positive. This is where the current's gonna go. Now take a look. Don't even copy anything down yet. Just take a look what's happening. So the current's gonna come from the positive. Look at this. This is gonna be, I'm gonna call this one R1 and this one R2. Okay? So what happens now is when the current, so here is the current, I'm gonna call it the IT. Do you know what IT is? This is the total current that's coming out of the battery. Okay? When it reaches the R1, we're gonna call this one I1. That's how much current is gonna go through the R1, okay? So some of it is gonna be used up here, but look, remember I told you yesterday, before you actually turn on this resistor, it actually has to go all the way back to the battery first. It has to complete a circuit, just like the water, right? So this is gonna be your I2. Then because it's the second resistor, we call it R2, so then it will be I2, right? So take a look at how many paths the current has to take to get to this one. Same thing with this. You got the positive here, okay? You got this way, this I'm gonna call R1, I'm gonna call R2, so this will be your I1, this will be your I2. So it goes this way, goes through the R2, and then back to the battery, okay? So how many different roads can you take to go back home? Imagine this is home. This is home, right? Think of it as the battery is the home. At the end of the day, you want to go back home, right? So look at this. This is one road. It goes through R1. That's one road. It's still one road. Still one road. There's no other turns. Can you turn?
No.
You turn this way, but there's really no other way. There's no choice, right? Is there a road here? Can I go straight? No, there's no road here. Can I go to the right? No, there isn't. So in a series circuit, the series circuit, there is only one way or one path for the current to follow to get back to the EMF. What do I call EMF? What's EMF? So from now on, I'm gonna call that EMF. What's the EMF? The V, okay? So this is the EMF right here, the source of the power. The power source is the EMF. So you put the voltage right here. So if you only have one path to follow, then this is a series circuit, okay? Because the two resistors are connected this way, one after the other. If the current in one resistor is interrupted, the current is also interrupted. Okay, what does that mean? If R1 is off or broken, what would happen to R2? Can R2 turn on?
No.
Why not? Remember, if R1 is to be turned on, that current has to go back to the battery first.
Because it goes through R1 first.
It has to go through R1 first, right? So if this R1 is broken, so let's say I cut this wire or I broke the light bulb, that means the tungsten wire inside the light bulb is now broken. R2 is not gonna get any current at all.
Yeah.
Because the current has to go through R1 first. It has to be slowed down by R1, the monster fangs, right? So R2 does not work. Okay? What about if R2 is off or broken? What happens to R1?
Doesn't work.
Does not work either. So I'm just gonna write this once. So basically if one of the R's or if one of the resistors is off or the switch is off or broken, meaning there's a broken wire somewhere in the line, okay, nothing works.
But still, current is in R1 now.
If R1 is off,
No, for example, R
if R2 is off, it won't even turn on R1.
current circuit or just battery?
So what happens here is it actually will not even run the current. There's no current at all. It won't turn on. So let's say I touch the wire here. Will I get electrocuted? No, you won't. You will not get electrocuted. You have to do this. You have to touch this wire right here, and then you have to touch the other wire that's connected to the battery, and then you'll get electrocuted. So in other words, you see this outlet right here? You know this outlet, how many holes do you have in your outlet on your wall at home? You got 3, right? So you got your outlet looks like that, like this, right? And you got one here, and then you got one that's slightly longer, and you got one that looks like that. You guys know this is what your outlet looks like, right? It's like a happy face that's winking at you. One is slightly larger. Do you know why? What are these things? One is negative, One is positive, and one is ground.
Ground, yeah.
It's an extra wire that they put there. So you actually have inside, you actually have 3 different wires. Looks like this. So they wrap it around, but each of these wires are insulated. They cannot touch each other. So you have a positive wire, a negative wire, and one is not, it doesn't do anything, but it can actually prevent you from getting electrocuted because it will take it to the ground, or it will prevent the device from overheating, or it can prevent fire. So it's a good thing to have that ground. Okay? So that is what a series circuit is. It's all or none. So basically we can say that a series circuit, it's all or nothing. Okay? It's either all working or nothing at all. Okay, so let's take a look now. What if, remember we also have a switch? What if I put a switch right here? Let's say I have 2 light bulbs, right? I switch this one off. I switch it off. It's not broken, okay? The light bulb is still working, but I just turn the switch off. What would happen to R2?
Does not.
Doesn't work either.
It means that.
Right, because remember, the switch means you actually have 2 wires like this. When you switch it off, it actually opens that bridge. So you can't get the charge to go through. You can't get current running if there is no path to follow.
It means if something will happen, all is not
All off. Yeah,
Totally, if something happens.
that's right.
Nothing goes.
Here's an example. Actually, some of our lights are in. So you see here, I'm going to turn this. These are all on, right? Take a look at the lights. I'm going to switch one on. Okay? You see what happens? Which ones are connected? Is that one on?
That's on.
So that and this are connected to this wire, right? And then the other switch is just that one, the last one by the girls over there, right? And also something happens here. Take a look what happens to the projector. Okay, look at that. See that? Okay, now I'm gonna switch one off.
Yeah.
Something happens, so they are somehow connected, but they are not connected in series. If everything here is connected in series, I turn this off, everything goes off.
Parallel.
It means there is 2 threads.
So there is a different connection here. So these 2 are in series. We know these 2 are in series, right? But they are not in series with that one, so we call it parallel, which is our next type of circuit. Okay? So now we're still talking about series circuit here. So there are 3 cardinal rules. Cardinal rules, meaning these are the ones that are always true. That's right, only one path to follow. So in a series circuit, we're going to summarize this now in terms of current, volts, and resistance. So the current in parts of all the series circuit, it has the same magnitude. So here it is. So the total current is going to be exactly the same. So that means that I'm going to use an example here. So it says an example. So let's draw one. So let's put R1. Let's put 5 ohms. So that is the unit that we use for resistance. It's named after Georg Ohm, Simon Ohm. Okay, let's say R2 is 10 ohms. And let's do 3 resistors. 15 ohms. Okay, the EMF, total voltage or EMF, is, let's make it 12 volts, like your car battery. Okay, so this is in series. Do you guys want to draw this one? Let's draw 3 resistors in series with each other. So go ahead and make your diagram. You can do it any way you want. So I'm going to put my R1 here, R2. Okay, so this is what my drawing looks like, okay? So how does that work? Did you guys draw your diagram somewhat? Now you go with your diagram. If your diagram your schematic looks different than mine, go with yours, okay? But we all know that the current is gonna come out of the positive terminal. So I'm going to trace my positive terminal right here. That's where the current's gonna come out, okay? So here is gonna put some current into this R3. So in my picture, R3 is gonna get the current first. I call it I3. So guess what happens to that? Let's say the total current is 5 amps. Let's give it a high amps right there, 5 amps. Remember R3, what's R3 is 15 ohms. And this one here is 10 ohms. And this one is R1, oh, R1 is 5 ohms. Okay? So what do you think happens to that 5 amps? Well, let's go back here. Let's go fast forward for a second. If I am putting out 5 amps coming from the battery, how many amps must come out? It's also gonna be 5 amps. It's 5 amps for the entire thing because the current is going to be conserved. Charge is conserved, remember? So what do you think happens to this current that goes here? This is gonna be 5 amps. Look at this. It's gonna use up 5 amps. R2, which is now called I2 in terms of current, is also gonna be 5 amps. And I1 is, guess what? It's still 5 amps. So the charge, which results in current I, is just going round and round and round, and nothing is changing. So this is the easiest one to analyze in a series circuit, because in a series circuit, the total current is exactly the same as current number 1, number 2, number 3. Doesn't matter how many resistors you have. So the current stays the same in a circuit. Current is the same in series. In a series circuit, nothing changes. And guess what? We don't even care whether we have 5 ohm, 10 ohm, or 15 ohms. They're resisting with different strength, but the amount of current remains the same. Okay? It will make more sense later on, but right now all you know is that what we know here is that you have this path. It's just gonna go through. That's all it's doing. It's just going through in a loop. What about the battery? The voltage. Okay, so here's the voltage. What's happening here? What exactly is a voltage, right? So just to kind of review what is a voltage, voltage is potential difference. So that means you gotta have a potential difference. You gotta have a difference here. It can't be the same then, right? So the potential difference then is basically what? So voltage is what kicks the electrons out of the EMF. So you have your power source. The power source could be an AC, the outlet, or a DC, a battery. And what kicks out the electrons is what we call the voltage, the potential difference. Which means in terms of the positive and negative, okay? So when the current comes out, well, that's coming out because the electrons are being kicked out, right? Let's say you push it out with 12 volts. What has to come back has to be 0 volts. And you see the difference right here? There's the potential difference. So you want to actually use up all that kick, all the pressure that is going to get the electrons to come out. By the end of that cycle, by the end of that loop, whatever loop that is, series or parallel or combination, it has to come back with 0 volts. Okay? Think of it this way. So let's say I'm an electron. I get kicked out of the wall with 120 volts of pressure or push or kick, right? So I'm running full force right here. So as I come out of the battery, I will have more volts right here. So if you take a look at these guys here, they're gonna get different amount of volts. They're gonna get different amount of kick depending on how much resistance they're going to resist, right? So that means that if you guys are going to resist me with the same amount of pushback or resistance, right? As I go through Adam, I'm still stronger, right? By the time he fought me, and then I go through Adam, and then now I'm fighting Michael. Michael Hale right here is gonna fight back. So I'm gonna get more tired because I've already fought one guy. So by the time I get through you, I get through Michael Tesfagergis, I'm gonna be more tired. So by the time I'm finished with Amber, I have no more energy left to get back to the wall. 0. Test for Michael.
Yes, that is my grandfather name.
There you go. Because you know what? I had another student before with same name but Tesfagergis.
That's why I know. That is my grandfather name. My father name is Araya.
Oh, okay.
As in Canada, like that.
All right, so let's analyze this actually with our example. So the voltage, so if you're starting with 12 volts, the sum of the voltage that they're going to get will be equal to how many volts? Well, our V1 plus V2 plus V3 is going to equal 12.
R2 it will be the same 12.
So this will be,
It will be 12. More 12 until
well, how do we know that? So this, I'm going to call this one V3 now. This is V2, and this will be V1. Okay? So how do we now know? They're going to split unevenly, right? So we can actually now use V equals IR. Ohm's law then will come and help us out in this case. So what's I? I is 5 and R is 15. Okay? So what's that? 5 times 15 is 75. Wait a second here. You got 15 ohms, 5 amps. Okay, so I completely made this up. The total volts will actually be not 12. So I'm going to erase that because I can't make up 12 volts and then give it 5 amps. It's not going to even up, right? So I'm going to just take out the 12 volts for now. We can actually figure out how many volts is actually going to be there. So this is 75 volts. What about this one here? IR. So I2, R2. So I is 5 and the R is 10. Yeah, 10 amps, right? So this will be 50 volts, right? So what's our V1? So 5 still times 5 is 25 volts. So our EMF is actually not 12, obviously. It's going to be the sum of these individual ones. So the total voltage is equal to V1 plus V2 plus V3, which is what? 75 plus 25, which is 100, plus 50. It actually is going to have to kick it with 150 volts. Okay?
I have a question. So what if suppose voltage becomes 0 at the end?
Yeah, so then 150, think of it this way. So here's what's happening. So you're giving it 150 volts from the positive terminal, okay? Look at it, look guys here. Let's trace this, let's trace it. So 150 volts coming out this way, and then you're gonna, it's called the drop, is gonna drop 75 volts into R3. So what's gonna be the voltage right here in that wire? Is gonna be 150 minus 75, which is 75 volts remaining. So now it's gonna go and power up R2. So it's gonna drop only 50 volts. So what's gonna come out of it?
50.
It's gonna be 75 minus 50. It's gonna be 25 volts left. So what's gonna be in this wire is gonna be 25 volts right here, which will then be used up by R1. So by the time it gets back to the EMF, there's no more. It's gone. It's used up. Okay? Remember, voltage gets used up. Current in a loop remains the same. So if it's a series circuit, which is just a loop, it's a very simple loop, the current is going to be the same regardless of the resistance, even though the resistance have different ohms, okay? We don't care. 5 ohm, 10 ohm, 15 ohm, they're all going to take the same amount as the total 5 amps. But the volts is going to be split amongst them. Okay, last thing that we need to look at is the total resistance. This is a series circuit, so it's easy. You just add them all up. So straight adding in a series circuit, just straight addition. Okay, so the more light bulbs you have, for example, the more resistance you're gonna have. Well, you're just gonna add them all up, right? So let's find the RT. RT is the total resistance of this. Will be R1 plus R2 plus R3, which is 5 plus 10 plus 15, which is 30 ohms. So we have a total of 30 ohms. The entire circuit is going to resist with 30 ohms of resistance. So now, with our example, we now know the individual resistance, which is given, but we've just calculated the total resistance. We know now the individual volts and the total volts, and we now know the individual current, which is the same as the total current in a series anyway.
If you multiply the total resistance times current.
Yes, if you go V equals IR and you want to know the total, you're gonna have to use the total of everything. So if you wanted to, let's say, find the total RT that way, you could do that. So if you're looking for RT, then you go VT over IT, because we know the VT, which is 150 volts. You divide it by the total I, which is 5 amps. What's the total resistance? Still 30 ohms. So that's another way of finding the R or the VT or the IT, whatever it is that is missing. So far so good? Okay, so before we switch to parallel circuit, I'm gonna get you guys to practice with simple series circuits first, and we're gonna practice that, solidify our series circuit knowledge, and then move on to parallel.